Dr. Anirban Bandhopadhyay is a principal research scientist at the National Institute for Materials Science, Japan. He did Ph.D. in IACS, Kolkata, 2005. During 2005 to 2008, ICYS Research Fellow at NIMS, Japan. In 2008, joined as a scientist at NIMS, built organic jelly-based artificial brain, quantum computer, molecular motor-based drugs, brain-inspired computing, and written a book named Nanobrain, The Making of an Artificial Brain from a Time Crystal in 2020. From 2013 to 14, visiting scientist at the MIT, USA. Hitachi Science and Technology Award 2010. Inamori Foundation Award 2011 to 2012. Kurata Foundation Award and Sewa Society International Member, Japan, and published more than 100 papers and 23 patents and edited 17 books. And we are honored to have you here, sir, to deliver a lecture on Toward a Modular Soliton-Polariton Quantum Supercomputer, Channel Scale Architecture, and Invariant Network Formalism for Quantum-like Big Data Analytics.
The Soliton-Polariton condensate, this is a concept that is that started in the 1980s, and the Soliton is considered as Soliton concept came in 1820, several years back, and it is you have a canal or a pathway, topological path, through which if you create a ripple of energy, then it can pass through long distance without any dissipation. And polariton is also when photon binds with exciton. Exciton is also a quasi-particle. So what are these quasi-particles? Quasi-particles are when, say, we have an electron, and electron excites from the valence band and goes to the conduction band, but the energy is not sufficient to go and travel through the entire material. So what it does is creates a binding force between the two, the empty space and the charge. Now this quasi-particle, say polaron, polariton, or exciton, all of them are quite different in as far as physics is concerned. So without getting into the details, because these are known for more than 50 years, I would like to tell about their features in biological systems. So in around 2000 to 2005, during this time, you will find a huge number of literatures that are coming up describing that how these quasi-particles could be used to build a very particular directed transmission across the system. In the screen, you are seeing microtubules, and these microtubules are a kind of nanoware, 25 nanometer diameter, and several hundreds of micrometers long width. And they, it has been proposed that they transmit soliton. It has been proposed that they generate polaron and polariton, and Soliton-Polariton condensate like features have also been proposed already. So I would like to describe Soliton-Polariton condensate as it has been observed in the biological systems. There are several ample cases in the normal systems, and then I will talk a little bit about the computing and how we can use Soliton-Polariton condensate in the computational processes. So if we try to implement Soliton-Polariton condensate in computing, first we look into the we look into microtubules different parts. So to the right hand bottom, you see a scanning tunneling microscope image. So to get an evidence that there is a Soliton-Polariton condensate, you have to send a set of light and at different frequencies. And when you find the absorption and absorption emission spectroscopy, you will find sharp peaks at a certain frequency region of optical light. So from which is a preliminary evidence of Soliton-Polariton condensate. But there are several other evidences. For an example, you can look into the quantum tunneling image, and you can excite it with photons of different frequencies. As you can see to the right, we have excited the microtubule with the different frequencies and took the quantum tunneling imaging, because whenever you make a condensate, say Bose-Einstein condensate, then the best way to prove that there exists a condensate is that you excite energy. And when you excite with certain amount of certain frequencies or energies, you find that that there is a symmetry breaking of clusters of condensates. So when you can switch from one condensate cluster to another condensate cluster, and the symmetry breaks from one to another, then that is another evidence that there might exist a Soliton-Polariton condensate. Of course, you have to do NMR, you have to do Raman spectroscopy to find out the free charge and other correlations and density of dipoles, and apart from the density of electron density of states. So these are the kind of basic experiments that are performed to confirm Soliton-Polariton condensate. So Soliton-Polariton condensate synthesis is not a new concept. It's very old. I'm not claiming that we are the first one to observe it. There are many evidences in many complex materials, complex structures, and there are different branches, different schools of physics, which addresses different parts of this problem of forming Soliton-Polariton condensate at a room temperature. But how can we use this in computing? So let's we go into the single protein structure and even a monomer. And if we look at the quantum tunneling imaging and we try to excite the structure with the different frequencies, then we can find that the whole molecule changes in a different way. Normally, we would think that this is change in the local density of states because we are measuring the quantum tunneling images. However, if we excite it with photons of different energies, even then when we find that there is a transition from one symmetry to another symmetry, there could be a possibility that Soliton-Polariton condensate is being formed. So we try to understand the origin of this condensate formation on microtubule-like structures, because when we build the computer, we will be inspired by the helical nanowires that we have. And from the helical nanowires of microtubules or alpha helices or DNA, we will create a helical nanowire gel, and that will be using for the computing. So whenever we have a situation that the condensate is forming in a gel structure or a cluster of nanowires, then we should not, for quantum information processing, we never look into the amplitude, because amplitude, if amplitude entanglement, superposition of amplitudes and amplitude-based computation and other processes are carried out, then there is a problem. Problem is the expenses go very high, and amplitude for any interaction, amplitude gets changed. And it is better to rely on phase, because by squeezing the photons, we can create we can squeeze the phase of light, and we can create a quantum light to read the condensate. And if there is a condensate formation, how the information is being stored or how the information is being processed, we can read it live by shining a light of a quantum nature. And when we do that, we don't look into the amplitude, but the phase shift. Why? Because if we want to prove that there is a quantum information processing, then phase shift is a very credible, easy, and a low-cost way. Low cost, I'm talking about low cost many times. The reason is that suppose you are working in a laboratory, in a quantum optics laboratory, and you want to understand that there is a quantum information processing, and I would like to only look at phase. When you look at phase, the raw data, or the first order information, there is always a chance that there is an error and you encounter error. That's why you have to cleverly redesign the quantum circuits so that you can look into the phase shift. And when you look into the phase shift, the first order, perhaps you remember in earlier days, in the 1950s, 1960s, when we used to do current voltage measurement, what we used to do is take DIDV, differential of current and differential of voltage. Why? Because then the electrode that is there, its effect could be neutralized. And if you take D2I, dV2, then you could get double differential of current and voltage, then you get the vibrational spectroscopy. Similarly, if anyone wants to do quantum measurement, then differential of phase is a very credible way to eliminate the effect of the circuit, because quantum circuit is a very big fallacy. You may think that you are creating an entangled source, but every time you pass through a beam splitter or something, or quantum coherent regions, every junction you encounter, there is a possibility of generating an error. And we need to find out a protocol to observe information. So that's why this particular protocol that you are seeing in the screen is a very important one. Why? Because suppose there is some event that is happening in nature or around you, and there are four kind of events that could be quantum-like, superposition-like. Several variables are interacting with each other. And if you change one, all others change in a typical way, non-algorithmic way, non-computable way. And this each sphere that you are looking into could be a variable, where you can where you can where you can understand that in an unknown data, suppose you are looking into cybersecurity data or internet, large transmission of data, or a genetic algorithm, genetic data, where mutation is happening, or a drug interaction, and you are looking at the transcriptomics, how the DNA and RNA is changing. So all these are big data, big data, and often these big data change rapidly with time. You do not have any time left to understand the whole data and write an algorithm. So what we would like to do is to look into the variables, integrate them in terms of their phase, so relative to each other. That means, suppose I get up in the morning and I eat, says at 7:15. Only after 5 minutes, I go for a morning walk. So, the gap, 5 minutes between my breakfast and going for a walk. So that is that time is converted into the phase shift that is happening between the two events. So regular events are spheres, and relative positions of the spheres tell us that how they are correlated. So it means, suppose there is a periodic event, and on a sphere we can put them, then on the surface of the sphere we can make a hole, a singularity, and then you can put another sphere. Now those who are working here on quantum computing or quantum information processing, they know hyperspace. You already know, because I understand that all of you present here are very well versed with quantum computing. And so you know that linear, non-linear, logarithmic, no, or differential. None of this relationship gives you quantum. Only representation that you can get is by hyperspace. So if you want to create a information structure in continuous variables or discrete variables model, it's better to concentrate on creating an information structure where two different, say, block spheres are connected by a singularity region embedded onto each other. What is the advantage? Advantage is that you can model the hyperspace where the hyperspace means if someone not from quantum computing, I square equal to -1, so a plus ib whole square is equal to a square minus b square plus iab. So this minus b square is actually coming from the hyperspace and changing your reality. So quantum mechanics, origin of quantum mechanics, no one knows. I also don't know, and nobody knows in the world. But we know how to use this technology. And when a plus ib whole square, I'm saying it, that means what we are trying to do is how hyperspace is changing the reality, the physical reality that we want to model. So in the information structure, we put the embed the spheres. Now let's get into real helical nanowire and how it has many periodic oscillations. And when there are many periodic oscillations, how could we check that there is a information processing that is going on, many periodic oscillations. For an example, I was showing a nanowire, a helical nanowire. If I go inside one protein, we find many different nanowires. So if these are the kind of situations I have, then all the different events, periodic events, coming together and creating a model. And relative dynamics is the solution of the problem. I repeat, suppose somebody asks you that I am giving you an unknown phenomenon which is changing rapidly. You don't have any time. So you understand that if you want to solve it, then you have to identify all the variables or invariants and link them together into an integrated structure. So this is what we call polyatomic time crystal. So it means I have a big sphere, which is very slow event that is controlling all the dynamics. And then there are relative events, which are controlling partially different part of it. So in this way, we can understand that how the event would unfold and we can explain it. So one channel, if I have a helical gel nanowire, where each helical nanowire could represent a particular type of clock, and millions of such helical nanowires come and form an assembly and replicate the quantum event that is the unknown data has been encoded into the gel, then we could have a model. But that is computing. But recently a new concept has come, that is modular quantum computing or modular or supercomputing. And so what is that? You have many, the sphere that you are seeing, it is a model that it has been created. But how it has been created? You take the data from the environment, find out the periodic events using a classical computer, find out those classical events, convert it into frequency, send it to the gel. Gel creates the supramolecule, just like transfer matrix T, TMT. And that is actually a nested set of spheres. Each sphere represents a variable, and the geometry that remains unchanged because of this is the invariant. So that is the computing all about. So in this way, what we have done is we have tried to see that if we want to create 1024 channel quantum supercomputer, so one channel can give us only one protocol how we can solve a problem. One thing that I would like to say is that one computer, one gel or one channel quantum computer can solve a problem. However, you can see only one type of protocol. In quantum computing, the biggest challenge is the protocol that you are using to analyze the data is fixed because of a circuit. In classical computing, this is the same problem. So what you need to do is to have another. So many different parallel processing by which you do that. But in quantum, parallel processing is not going to work. What you have to do is all the channels for modular supercomputing that you have, they need to be connected together. There should be a transfer matrix connecting different polyatomic time crystals that you are seeing. In this case, 16 channel, but we targeted not just a 16. So I will get back to the from 16 to 64 to 256 to 1024 channels, but stacking them one after another. But we have to include, so quantum supercomputing or modular quantum computing, where different protocols, say 1024 protocols, 1024 different situations, and simultaneously get a snapshot. So that is kind of a very high form of quantum computing, where imagine that you have 1024 quantum circuits and they are all linked together. So we have carried out theoretical simulation. We have not experimentally built it, but we have built until 14 channel, a 16 channel quantum computer in Japan. And then that one has the principle something like this. In the top row, you can see that antenna is sending the signal from the top, and antenna is taking the input, say whatever be the input, and then it is sending to the gel the set of variables, and organic gel is synthesized, and that organic gel, from the organic gel we send the light, form Soliton-Polariton condensate, and Soliton-Polariton condensate doesn't survive for more than a few picoseconds, tens of picoseconds. So basically the snapshots that we take continuously, and finally we build the solution structure by analyzing the photonic structures. So basically, there is a helical nanowire, and helical nanowire changes its length, pitch, diameter, and the light falls and then creates a vortex. Depending on the property of the vortex, we identify what are the different features. So we created a Hamiltonian for the special different purpose. Every single group, whatever the material they use, they build their own Hamiltonian and quantum mechanical model. The reason is that every single material, the way we are using it for the quantum protocol, where everyone has to build their own Hamiltonian. There is no other choice, because unless until you are replicating other groups' work, because your material varies, accordingly your wave function, basis sets, everything would change, and correlation map you need to create. I see many people or many different groups who are making quantum computers. They use wave functions from Xanadu or others, strawberry fields and something. This is not right, because the kind of optical circuit setup that they have based on their density matrix, they have created their own wave function. And I find many researchers, they just simply download the strawberry field and then they go on understanding it. My suggestion is always to take your own system, understand the features, and build your own Hamiltonian, so that you can connect it to the density matrix, and that is most realistic one. So in the initial days, of course, you can take other groups, but you have to always understand that is scientifically incorrect. And so we went on understanding the typical features of the Hamiltonian for helical nanowire. And you can find H equal to H1 plus H2 plus H3 plus H4. Just look at it. Only in these two rows, you will find that there are 2 point contacts from the top and 2 point contacts from the bottom, and then they flip-flop. So this is how a unique ability to modulate the optical vortex or condensate formation is possible. So whenever you are trying to build Soliton-Polariton condensate or room temperature B condensate, because if you want to build a room temperature quantum computer, you need a way to create quantum circuit using this. Now, there are many basic experiments that are performed, and vortices are measured. For the last few minutes, I will talk about how the computer is actually created. So basically, this is from our published paper. Yeah, we published it as a neuromorphic computer in the beginning, and later advanced it into a quantum computer. Now we are going for quantum modular supercomputer. So the cheetah video enters into the organic gel at many layers, successive layers of fractal structures. So helical nanowires come and then they assemble and assemble and assemble and assemble. And then from their optical output, we find out and retrieve and rebuild the cheetah. So initially, when we looked into this, it was apparently a very classical computer to us, and we published it as a classical computer. Later, when we went deeper and tried to understand in a much more profound way, then we found that we are getting a much better understanding of the computing. So we create a special kind of hologram to capture, because please understand that one of the biggest challenge for quantum computing is non-demolition measurement. So it's very nice. In 2002, I would like to say that there was a concept of atomic switch. So crossbar architecture, you know very well. In crossbar architecture is the way in the 1980s and the 1960s, the 70s, it was the era of development in which you address every single switch in your processor. But in quantum, if you try to do that, there are many problems, because every time you read it, you add error. Even though you say I create eyeglass state, or I create a buffer state, or I create a replica which will not be affecting the main one, uh, those kind of sentences are good to listen but difficult to implement. So what happens is, in our case, suppose what is the basic concept? So imagine a tree. Tree has many different fruits. These fruits are quantum-like variables, like tunneling. One fruit is one side of the tree, and it jumps into the other side of the tree, and other side, other side. If this kind of things are happening, each fruit represents a variable. So if you want to understand what is the dynamics in a dynamics of the intelligence structure of that and rapidly changing data, and very, very fast, you do not have time to write an algorithm, then what you do is you take the fruits, send it to the gel solution, and the gel solution creates all the branches of the tree until the single branch is found. That is, from fruits, you make a journey through the different stems connected to the root. When you come to the one, this is called a transfer matrix tree, TMT. So once you have this, the computing automatically halts. So that halting problem you can solve. And not just that, once a tree is created, next time when you give any unknown set of combination, the tree knows, and to be best of its abilities, it will be able to, within a few steps of the branches connecting to the fruits, it will be able to tell predicting the future. So we create this hologram to take the Soliton-Polariton condenser that is forming in the gel out, and then study or replicate it. I would like to show you some examples of computing. So in a real world scenario, you see computing like this. So the cheetah is moving and a gel is forming. Slowly gel is growing. From the gel, optical vortex hologram is produced. From optical gel hologram, you create the 3D clock assembly of polyatomic time crystals. You analyze that by difference spectroscopy, and finally you generate the output. So in this way, different layers of invariants are created. So once you learn, it's a single shot learning, because you create transfer matrix tree. I have removed all the mathematics, but I mean, once the GL learns about four-legged animal, it can detect several four-legged animals with comprehensive in a comprehensive manner, not 100% accuracy, but at least some features are extracted. So that is what we want. We do not want to build a quantum computer that gives the accurate 2 plus 2 is equal to 4. We want a rapidly changing quantum-like information that is being processed or changed we can detect some feature and predict the threat or outcome and warn like a cybersecurity system or military defense system or other kind of systems. So so we took several benchmark problems and for an example, train with one dog and then find out all different features of the dogs. We took many different classes of problem. All these are published. So this is collected from the supporting online material of our neuromorphic computing paper. That is, if there is a cheetah, if there is a coronavirus dynamics of 18-20 years, how it evolved, and how diabetes data for 40 years were changing, and then you find new kind of dynamics. You try to find out from a complex Indian song what could be the Indian raga, flock of birds or swarms, what is the dynamics in them? Is there any intelligence at all or not? Then pouring water, then workers, whether they are working in the factory or not. So similar kind of problems are there. So basically what we are doing is we are creating a fractal tape in the organic gel, and we are taking an information, going inside, expanding it, and going inside and expanding. We call it a fractal tape. So instead of Turing machine, we could say it. Now we have come to a situation when we end our journey by suggesting that we have already started constructing 64 module quantum supercomputer, where we have 64 different polyatomic time crystals generated from 64 different gels, and they will be integrated together, and their collective information will be taken out. Why 64? 8 different types of protocols by which I take the variables. For an example, you can take the variables considering that there is a large periodicity of events that is happening in the universe, and if you go inside and inside and inside, you find cascade of periodic events. That could be just one protocol. It could be that you detect the objects and there is a topological matching of different parts of the data of the unknown information. Because this kind of quantum computer that we are creating, we are trying to find a proper use case. And in our case, our claim is that the proper use case would be quantum-like events that are happening every moment in nature. So we take only causally related event, the cause and effect, or periodic set of events that are all connected together, and they are generating events one after another, and coming back and forth. So other than this, we do not use any other format in our algorithm creation. What if you have a retroactive features? What if you have a quantum tunneling length features? As I said, from one side of the tree, when one fruit jumps into other side of the tree, or transforms into banana in a mango tree. So if this kind of situations that are happen, that is non-algorithmic, non-computable, in this kind of scenarios, you can use the kind of quantum computer that we are proposing. So 8 different types of protocols to collect the variables in 8 different ways, and 8 different kind of perturbation. So 8x8 magnetic perturbation. I think those who are building quantum computer know this very well, because magnetic perturbation is the most feasible way to perturb a system without affecting much. So after this, we will be going for 256 channels. Why 256 channels? Now 4 different kind of gels we will be using, and finally we are trying to build a 1024 channel quantum supercomputing modular. So in this case, 8 protocol for 8 different protocols to create the polyatomic time crystal, and 8 different protocols for magnetic perturbation, and 16 different kind of gels. So it means 1024 different gels, 1024 different quantum circuits will be produced, 1024 different ways the system will be probed, and simultaneously you will get the output. Because if you have one computer, you have one psi, and that psi density matrix, or if you do if you can do quantum tomography and find the density matrix. That is a kind of a solution of the problem that you are addressing. But if you have 2 channels, 3 channels, 4 channels, or 1024 channels, you get the same eye, because quantum technology is all about preserving the psi. And whatever be the processing that you do, the sanctity of psi needs to hold in whatever be the quantum circuit that you design. So so psi doesn't change. What happens is psi or the transfer matrix tree that we want to optimize in 1024 different variable way. So this is very ambitious project. Currently, we are theoretically investigating all this. And I would like to thank Nishant for inviting me to this talk. And I hope that because last time when Nishant invited me, I talked in detail about organic jelly and its computing. So today I have brought you 2 concepts. One is modular quantum computing, where you can and have many different kind of protocols, put them together, and Soliton-Polariton condensate. And what you do is Soliton-Polariton condensate a particular gel actually replicate a particular transfer matrix tree that can link the unknown events that cannot be algorithmically connected. And these two new concepts compared to my previous presentation in the conference, I would like to share. And thanks once again for listening to me for the last 45 minutes. Thank you so much.
Thank you, Dr. Anirban. We have a question. So the first question, there are 2 questions by Dr. Sovik Roy, Associate Professor. The first question, by hyperspace, did you mean n-dimensional Euclidean space?
Okay. See, Shovik, um, uh, when we say higher dimension, there are many different concepts of higher dimensions, and it is so confusing for us physicists and you and all the professors in the world. Very confusing. For an example, I'm talking about, say, logic gate based qubit based quantum computer. Okay, then 360 degree by n. So it's a sphere, and radially vectors go outward, and 360 by n, that is the solid angle, and that is the kind of concept of dimension. So if I have say 6 dimensions, 360 by 6, so 60 degree solid angle around a sphere, there will be a radial vectors. However, when you go for, say, string theory, same physics, but you find that 10 dimension of space-time. So even how do you define the spatiotemporal features? You make it 10 different ways. So all the features, I would say that your question is very good. I think those students who are listening to this, for them it will be very helpful. That if I come up with a concept, whatever be my concept, doesn't matter. Okay, so there is another concept like XYZ orthogonal to each other. So if you want to create 4th dimension, you just put a line anywhere, and you say that it is orthogonal to XYZ. And then if you want to 5th one, then orthogonal to all 4, orthogonal to all previous. All these concepts that you are doing in a different space time, when you remain within the domain of space time, it doesn't matter what are the tricks you play. You are already in a real space, in reality. By hyperspace, I'm not talking about n dimension. You can define many different ways. I'm talking there could be only one dimension, but in the imaginary scale, non-physical realm, that actually affect your reality. So it is not about n dimension. By hyperspace, I'm talking about I, an imaginary spatio-temporal, beyond space-time. Whether should we call that dimension as space or time, it's not sure, but never space-time or space or time or anything, because what is there, as I said, that we do not understand how the quantum mechanics exactly works, but we know how to use it. So that hyperspace, how it is structured, how it is this, we don't know as of yet. Someday in future, if the origin of quantum mechanics is understood, and from a basic quantum mechanics, the formulations of quantum mechanics is derived, probably at that point of time, we will have much more understanding of the hyperspace that we are talking about.
Yes. Thank you, Dr. Anirban. We have another question. And I am very much interested to know, how do you take care of decoherence, noise factor in your experiment?
Uh, there are several ways how we can. I have not described it in today's talk. Um, uh, there are various different ways to take care of the decoherence. First is topological homology that we use. It is not said here. So I said that there is one phase, light with one phase. We could have light with three different phases. In classical light, you can have just one phase. But in quantum, you can add multiple different phases of light. But if you have three or more phases, then you can preserve the homology. That means, say, light has three different phases, say 120 degree, 240 degree, and 0 degree. Okay, so now one phase you can use for information processing. Another one is the idler state. So if during information processing or any interactions, what will happen is that the state will get get some error, and then from the buffer state you can link it in such a way in the quantum circuit so that it can correct the error. But if these two phases are interacting with each other, then both of them will get deformed. Then comes the reference, and the reference line phase we try to preserve throughout the system and connect it to the beginning. So when we optically reading the Soliton-Polariton condensate, we always use three-phase light. Our SPAD is three-phase, and then coincidence counter also we redesign it in such a way that we take the differential counting of the photons arrived, and also the three different phases, how they are changing and what are the correlations and the polarizations. So this is one aspect of how we address the correlation, because the question is very important. If we allow decoherence can be addressed I mean, I talked about only noise. So noise, not just that, there is a orthogonal feature. For an example, our input is microwave. Orthogonally, we apply optics light, so that is 10 to the 16 and the 16 hertz to read it, to melt the gel and redo the computing. That is 10 to the power 12 hertz. So 10 to the power 3 orders different with every single thing, and then we use orthogonal way to do each other so that the cos 90 degrees is 0. But there are many such tricks which are used to minimize the formation of noise. Regarding coherence and decoherence, there is a concept called Berry phase ladder. So Berry phase ladder is if you have a fractal structures in every single layer, and your frequency spectrum, say in our case, it is triplet of triplet. At every single spatial scale, we have it. So if you look at the phase quantization, if you do the calculation theoretically, you can contact me later, I can tell that. Then you will find that the phase that is 45 multiples of 45 degree is preserved at every single layer of the ladder. So this is how you can sustain coherence for a longer period of time. But please understand then that if you want to build a quantum computer, few nanoseconds of survival of coherence is enough. Few nanoseconds, you have to finish in few 9 seconds, unless until in future somebody comes out, because Soliton-Polariton condensate normally 10 to 15 picoseconds, but you can increase it with a fractal architecture, say few nanoseconds. But processes has to be completed in a few nanoseconds only. So we cannot have the luxury when we are making the quantum information processing to to hold the coherence, for example, microseconds. There are elements which shows quantum coherence for microseconds, milliseconds, but whether they are suitable, quantum material shows a high coherence time does not mean that it will be suitable for computing. And that is also another concern.
Thank you, Dr. Anirban. We have two more questions. Next question: how does the error behavior change as you go on increasing channel count from 2n to 4n and so on?
Okay, so as I said that currently we have not built it experimentally. Experimentally only 16. Okay, 1 to 16 we have jumped. So my answer will be only limited to 1 to 16 because we have not realized 60 because or to 264. Only theoretical simulation is going on different aspects, and we are testing it only on the very limited number of channels that we have studied. And based on that, I can say that I can say that in case of quantum systems, when you change the protocols, and quantum light is divided into various structures, the challenge itself is to preserve the topological homology, because it's if you have understood this quantum computer, it's a duality of homology and cohomology, because homology means completeness. I mean, not looking at the global part, but when from the tree fruits you try to find out the branches, transfer matrix tree, and coming to the root, then definitely you need to address cohomology. So what we do is this cohomology and homology duality, when it runs, only challenge for us is to hold the homology and reach the global homology at the end of the computing. So if we can preserve that, then even if we increase number of channels, it won't create any effect. So the challenge that we face always because depending on the quantum computing protocol that you are developing, your challenge for errors is fundamentally different. That's the reason it's very difficult to collaborate and expand for quantum computer, because you have to create an exactly identical system with exactly identical protocols for the next phase. So regarding your question that if I increase the number of channels, how it will be different, is preserving the homology is our challenge. It means if I have 3 different phases with 120 degree in same light source, in unique light beam that I'm sending as a quantum light, we would certainly have a problem, because every time we split it, and then send it to a completely different number of channels, we need to make sure that that the different phases are in a coherent relationship with each other.
We have a last question, Dr. Anirban. This is a question about consciousness. Some propose that the microtubule is responsible for consciousness manifestation. Could you please elaborate on this?
Yeah, so Roger Penrose and Stuart Hameroff proposed microtubules for consciousness. However, I mean, for the last 14, 15 years, I have carefully avoided this question. My answer is that technology has not reached to a level where we can create any model that can explain consciousness. The reason is that we have not created a model which tells us how our brain operates by itself. So self-operating mathematical universe, SOMU, that the proposal that we have made, because I think that humanity should first build an automaton, a machine that operates by itself, learns to write algorithm by itself, and and can survive in the environment by itself, doing everything by itself. So if we can have in future such a system, such a machine, such a organism like system, only then we can start talking about awareness. Because for awareness, testing awareness, you need a machine that is self-operational. So my target is to build and remain myself confined within the domain of self-operating mathematical universe, trying to understand how a system could operate by itself. When I came here today morning to give this lecture, I did not know what I'm going to talk about, and I had a general idea, but I was trying to put everything together because it's a summer school, and I was trying to be as simple as possible, not any complex equations or anything, and so that is the reason that that I tried to imagine what kind of audience could be there, and I was reformulating every moment my future approaches. So I am a perfect example, like all of you sitting over there, that we are a self-operating mathematical universe in itself, with a capability to encounter completely independent information, understanding with respect to global cohomology that is there, and with respect to that, determine our future course of action. So I think that for humanity, time has come for self-operating mathematical universe, understanding a machine that runs by itself, or a living organism. And at least I feel like we are century behind before making any attempt to understand and expand the concept of consciousness. Thanks to all of you, and thanks once again for inviting.